Welcome everybody to our third example of using the comparison and limit comparison tests for infinite series. So here we're asked to use the limit comparison test to determine convergence or divergence. Well, one thing with the limit comparison test, we have to have some kind of infinite series to know to compare it to. And in this particular problem, the solution that's given suggests that we actually compare it to our series that looks like 1 over n to the 9/8 power. Now, this series it is going to converge, that it is a convergent p-series. And we can go ahead and use the limit comparison test to go ahead and prove that. But one kind of problem or one kind of difficulty with this and using the limit comparison test is knowing which series to choose. And so kind of an open question or something that's reasonable to ask in this case is, how did we choose the power 9/8? And that one is kind of a difficult one to answer, and so probably in this case, even though we're asked to use the limit comparison test, I probably would not go to that first, mainly because of the difficulty in finding a series to which to compare it. And so what is probably more applicable in this case when we're asked to show this is probably to turn to the integral test. So what the integral test says is that we're given a series and we can come up with a function f that meets three conditions. Number one, that it's going to be continuous. Number two, that it's decreasing. And number three, that after a certain point, the terms of our series actually live on this function, then the conclusion is that the behavior of the integral from n up to infinity is the same as the behavior of the infinite series. Either they both converge or they both diverge. And so in particular, for our series, it's pretty obvious then what function that we can choose. That we will choose f of x equal to 5 natural log of 3x over x to the 5/4 power. Now it's pretty obvious that this is going to be a continuous function. Natural log is going to be continuous on its domain. X to the 5/4 is continuous on its domain. We're always away from 0, so we don't have to worry about 0 in the denominators. Everything looks great and awesome, and so we have a continuous function. It is going to be decreasing, so if we want to check that, we can take a look at the derivative to confirm that the derivative is always going to be a negative number. And so that will show us that, yes, this thing is going to be a decreasing function. And finally, it's because it's fairly obvious that our terms live on this particular function, then we've gotten our choice for the integral test. And so kind of checking all of those conditions, everything looks good. So let's see what happens then with our integration. Okay, so we're interested in this particular integral. Probably what we would do then to proceed is to say, well, let's just look at the integration itself. And probably with that, we would want to do an integration by parts. So if we just kind of take a second and don't necessarily worry about those limits of integration, let's just see what we would have if we try to do the integral. So for this, we want to do an integration by parts. And so we can see this as maybe an x to the 5/4 power times a natural log of 3x dx. So when we've got something involving a natural log, probably that's what we want to use as our u. And so our dv then just becomes everything else. So 5x to the 5/4 dx. So that our du then becomes a 1 over 3x times 3 dx, which we can just simplify that to just a 1 over x dx. Now for our v, we want to do the antiderivative of 5 over x to the 5/4, and so we would actually have, in that case, a negative 20 x to the 1/4 for our antiderivative. And so our integration by parts would then say that this is going to be u times v. So I have a negative 20 natural log of 3x divided by x to the 1/4 power. And then minus a minus is a positive times the integral of v du. So I have a 20 over x to the 5/4 power dx, which again, that one we can just integrate. So we have a natural log of 3x over x to the 1/4 plus a negative 80 over x to the 1/4 power. And so what we have then as kind of our answer for our integral, so we have a minus 20 natural log of 3x divided by x to the 1/4 minus 80 over x to the 1/4. And so the question is, what is our behavior then as x goes off to infinity in this case? And so coming back to our original integral from 1 up to infinity of our expression, we have negative 20 natural log of 3x over x to the 1/4 minus 80 over x to the 1/4 evaluated on the interval from 1 to infinity. Well, we know what that notation means, and in particular, that's going to be the limit as b heads off to infinity of a negative 20 natural log of 3b over b to the 1/4 minus 80 over b to the 1/4 minus what we get whenever we plug in 1. Well, the natural log of 1 is going to, so we're going to have in the numerator natural log of 3 divided by 1. So we have a negative 20 natural log of 3 and then minus 80 for that. So really what we're interested in is what happens to this expression as b goes off to infinity. Well, for our b in the denominator, one thing that we notice, at least for this term, is since we have that b in the denominator, that thing is going to go to 0. But then the question is, what happens to our natural log of 3b over b to the 4th? In that one, we recognize that we've got an indeterminate form of infinity over infinity. And so what that tells us is, hey, we're going to need to use Hopital's rule in that case. And so we look at the derivative of the top divided by the derivative of the bottom. And so we look at the limit as b goes off to infinity of, so on top we've got a negative 20 over 1 over 3b times 3. On the bottom, we've got a 1/4 b to the negative 3/4 for that derivative. And so if we clean this up a little bit, let's see what happens. So our 3's cancel out. So we have a negative 20 over b times, we've got a 4 on top, and we've got a b to the 3/4 on top. And so here we end up with an expression, limit as b goes off to infinity, of a negative 80 over b to the 1/4 power. And sure enough, we end up with a variable in the denominator, so we get a value of 0 in that case. And so that tells us that our limit is going to converge. So our integral is going to converge, and so by our integral test, our infinite series is also going to converge. And so our real conclusion is that probably the limit comparison test, maybe in my opinion, is not the best one to use in this case, but we do get that the series does converge. Series converges not by the limit comparison test, by the integral test. And so a big part of choosing the right test is being able to, can you directly calculate and get an idea of what the best thing is to use them. Sometimes with a limit comparison test, it may or may not be obvious. And so we might want to turn to some other test that we can use the series more directly rather than trying to find something to compare it to. So I hope you've enjoyed this one, and I will see you guys next time.